Good morning, everyone. Welcome to the day 3 of ESDP. Today we have our speaker. I give the dice to sir. Over to you, sir.
Okay, so good morning everyone. Today we'll be seeing what are the applications we can have AI in health, or you can more precisely say one of the applications of AI for health devices like hearing aids. Okay, so we'll see why hearing aids are important, what's the status we have, and where we can take it as a device when we are embedding AI in it. Okay, so why we need hearing aid? Because we can say that as per the WHO data, we are around 360 million people suffer from some kind of hearing impairment. Okay, some kind of hearing impairment means in India only we have around 62 million. Some type of hearing impairment or some type of hearing loss means we can categorize them. Okay, so we can basically categorize them in four different parts. It can be how our auditory processing unit is going to process the information, whether it is conductive hearing loss, whether it is sensory hearing loss, and whether it is mixed hearing loss. Mixed hearing loss is a conductive and sensory, both of them. Okay. Now, what will happen in auditory processing disorder? It means our auditory unit is not going to process the sound. So this is kind of permanent hearing loss. Okay. Then for conductive hearing loss is temporary. You can feel the same when you are in some DJ party or in some EDM night or in some rave. After that, you will feel that some of the frequencies are not audible to you. The reason is your threshold of listening is just shifted. Okay, for that particular frequency band. And the last one is your sensory hearing loss is kind of permanent hearing loss. Okay, so temporary one, it can be repaired or it can overcome in some after some time. Okay, so if you're coming from any marriage function or anything where the noise is very high, and or from some really you feel like you are not able to listen some of the frequencies. Okay, or you have a ringing effect. Okay, that is a kind of temporary hearing loss. Okay, and you will feel after some time it will you will start again the things are audible to you. Okay, this is because there is a temporary shift in the threshold of hearing for that particular frequency. So now, what is the solution for hearing loss? Hearing aid. Okay, hearing loss में क्या लगेगा हमें? Hearing aid लगेगा. Means we need some kind of aid. Okay, we call it hearing aid. So what we have? So hearing aid, if we see, and it might be possible, you all have seen ads of hearing aid at some places on internet. Okay. What they have one microphone, one loudspeaker, and what we need, as we are not able to listen some of the sounds, or we are not able to hear some of the sounds, what we can do, we just amplify it. This is a basic funda that we are not able to listen, so we put an amplifier and we just amplify it. Okay. This is what a basic hearing aid will look like. Okay. This will come in market in 150 rupees or 250 rupees, depend on different companies. It is just consists of one microphone, one speaker, and a gain control unit. Okay. Now the problem is जैसे बोलना बैटरी है 40%, कम हो गई है, maybe next session में लगेगी. Okay, so hearing is, this is the basic hearing. Okay, now the problem is it will going to amplify everything. Okay, there is no selection mechanism over there. I am coming from a party and or from a rally at only a particular frequency, let's say from 1000 hertz to 1200 hertz. Only that frequency is not audible to me because they are playing in that frequency range. Okay, and I am sensitive to only that frequency range. But what this will do, this will going to amplify everything. And because of that, other frequencies are also hampered for me, and the threshold for that one is also setting. Problem hoga. So why not we can program it? Why not we have different channels over here? So depend on the era of the technology. They started doing so initially in back 80s, they come up with the analog hearing aid. Analog hearing aid, this simple one amplifier, one microphone, one loudspeaker. Then they come up with a programmable hearing aid. Programmable hearing aid, the controllers will be digital, but the programming is in the analog domain. How? We have analog filters over there. From 0 to 1000 hertz, one filter, 1000 to 2000 or 3000, another filter. So we have different filter bands, and for each filter band, we have different frequency. If ये frequency हमें ठीक लग रही है, ये नहीं लग रही है, we can amplify only this one. ठीक है? We break down the whole into a set of filters. Then come into the picture of digital hearing aid, where we can make it more customized as per the user. तो इसमें क्या करेंगे? They first take the person for auditory, ठीक है, audiometric test के लिए जाते हैं, okay, and there they will check which frequency is not audible to that person, and accordingly we are going to just amplify that frequency. Okay, not everything, because rest of the things is audible to him. Rest of the things he can process nicely. Yeah. So digital, let me see. So this is how analog hearing aid will look like. A microphone, an amplifier, a receiver, a battery unit, and then we have some kind of gain control. Volume increase, or we can decrease the volume. Okay, this is our normal analog hearing aid back in the 80s. Still people are using, which is of cheaper cost. Okay, they are using it, 150 bucks, 250 bucks inside a plastic case. You can find it in Amazon, Flipkart, and India. Okay. Then we have this programmable hearing aids, in which still the processing is done by the analog, but control is by the digital. Okay, what we have some sort of different channels, frequency channels, and we can increase or decrease the gain of that frequency channels. Okay, and these frequency channels are nothing but analog filters. Still cheaper. Okay, but the problem is, it is once programmed, we are not going to change it. Okay, we can only change the gain. We can't change the frequency. Now comes to the digital analog filter. Here is the flexibility. We don't have to add any new component. Once the program control is there, we can reprogram it. We can keep on reprogramming it as per the need of the user. Okay. Every time we can go to the this hearing aid specialist, he will reprogram it as per the audiometric test they will test perform on me. So how the audiometric test they do? They will have this kind of remote. Okay, they will put a headphone and then they start playing tones, 100 hertz, and they will ask if you are able to listen that tone, then just press the button. Okay, 100 hertz, 200 hertz, 300 hertz, 400 hertz, till they will go to the speech range, 4 to 5 kilohertz. Okay, that is one way of doing it. Now, they check at what frequency I am audible. I am able to hear the sound. The next thing what they will do, they will start shifting the gain because they have to understand what is the gain I am able to hear. Okay. Then for the 100 hertz, they keep on increasing the gain and they are again asking to press the button. And accordingly, they come up with a more customized hearing aids by using digital processing technique. Once they have a data, they just put it over here. And accordingly, it is more customized for my need. Okay. So this is the type of hearing aids we have. Now, the type of technology we have in the hearing aid. Okay. Now the types of hearing aid. So if you search in the net or anywhere, you can see that basically we have these three types of hearing aids. One is behind the ear, which is the most usable. Okay. Why? Because it is not giving pain on my ear. If I continuously wear a in the ear headphone, I will feel like uncomfortable. Okay. Now, what is the problem with the in the ear headphones or in the canal? The thing is in the ear and in the canal. What will happen? If you put a finger inside your ear and you say anything, you'll feel like some low frequencies amplified. Okay, if it might be possible you have tried at your home also. If you put an empty glass on the top of your ear, you'll feel there is some sound is coming. That is the low frequency which is getting amplified. Okay, this is the same thing when we trap the air. Okay, when we trap the air, what will happen? It will going to resonate at some frequency. It is amplified. So these headphones are bringing occlusion effect into the picture. That is why it is not that much usable. Okay. Now this is the behind the ear hearing it will look like. We'll have a speaker over here. We'll have a microphone on the top of it. Okay. And we have the gain control unit. So this is how it will look in a simple block diagram. Microphone, amplifier, audio processor, battery unit, and volume control. This is the only thing we need in a normal hearing aid. Old one. Okay. Now what is the problem with this one? If I have only one microphone over here, it is going to pick sound from all the directions. Microphones are omnidirectional. Okay. So if I am saying anything and you want to listen only to me, what it will do? It is going to amplify sound even for the fan or the AC which is running behind it. This is not good. Okay. It is kind of a disturbing thing which is going to amplify all the ambient noises, but we want to focus only on the sound coming from the front. Okay? Coming from the 0 degree or coming from your direction of interest. You can say direction of interest. Suppose you and a person are standing in a conference hall and there are so many persons, people over there, and you want to listen only to the person standing in front of you. While cancelling all the sounds in the ambient noise. You can go for that possibility. Okay. So this is where we bring into the picture of how we can bring that kind of hearing aid which have a directional gain. Okay. Which can amplify sound only coming from one direction, not going to amplify from all the directions. Okay. So what is there inside a hearing aid? So one of the manufacturers is the Siemens who are making most of the hearing aids nowadays. Okay. If you are going for a professional hearing aid, it is by the Siemens which are programmable or more customized programmable is coming in somewhere in 70,000. Normal analog programmable is coming in 6 to 7,000. So what is there? We have a desired signal which is sensed by the microphone, which we need to be amplified. Okay, since we are using a ADC digital processor over here, so we need an analog to digital converter, and we want to play back into the real world. We want a digital to analog converter. Okay. In between, what we need? We need an amplifier. Okay. Now, what is the problem with this hearing aid? If anything is getting played over here, it will be picked by the microphone here also. So there is a feedback is coming. The same sound is feeding back over here, and it will keep on getting amplified. Okay. If anything is keep on getting amplified, what will happen? Will start creating a ringing effect. Okay. Guess what the ringing effect? Even we can check on this one. Yes, this is working. Okay, so what will happen in ringing effect? If the same sound, this is a microphone, we have a loudspeaker. Okay, if I'm saying anything and this is picked by the loudspeaker, whatever loudspeaker is playing again picked by the microphone, what will happen? It will make a loop. it will keep on increasing that sound. And after some time, what will happen? There is a limit. It is not going to play. And we have a single you might have felt this kind of sound when you are using a public addressing system. A single beep. That is the reason it will be coming because of feedback, acoustic feedback. Why we call it acoustic feedback? Because the acoustic signals are feeding back over here. So whatever I'm saying in the mic is played by the loudspeaker. Whatever loudspeaker is playing, again picked by the microphone. Keep on amplifying, and there is a limit. Okay. So we need to cancel that one, this acoustic feedback. So my desired signal is whatever the person is saying, which I want to listen, plus there is a feedback. So I want to cancel that feedback in the real time. Okay. Now here the update algorithm adaptive filter on neural network or your ML will come into the picture. How well we can cancel it. Okay. So when we are testing a hearing aid, we need some kind of quality measures. What is this quality measures? Quality measures are like भाई जैसे हम गाड़ी खरीदने जाते हैं क्वालिटी मेजर्स आर लाइक इट इज गिविंग 24 किलोमीटर पर लीटर दिस इज वन ऑफ द क्वालिटी मेजर और इट विल go from 0 to 100 kilometer per second in 0 to 100 kilometer in 30 seconds. This is one of the quality measure. In the same way, when we are comparing hearing aids, we need some kind of quality measures. The one is the misalignment. Another one is the Aesdp gain. The third one is the maximum stable gain. Aesdp gain is when we are providing, when we are using a hearing aid and there is a feedback cancellation. With feedback cancellation, how much stability we can maintain. Okay. This maximum stable gain is at each frequency, what is the maximum gain we can achieve without making the system unstable. Okay. So, so this is some of my research work where what we had done is like, why not we check the sparsity in the system. Okay. Sparsity in the system, whether the system is sparse in nature or not, whether the weights are sparse or not. Why we need so many weights? Okay. If I need to model this system, there is only this portion which is non-zero, the rest of them is zero. Why we need this many long number of taps? Okay. So we bring something as part of it in some of the results. Okay. Then the another work is we have done in the hearing aid is why not we divide the whole frequency band into subbands. Okay. N number of subbands. Let's say 0 to 100 hertz one band, 100 to 200 hertz another band. Okay. 200 300 hertz third band. Like this, I can divide the whole frequency into n bands, and I am going to put control for each 100 hertz band separately. So it will give me more resolution. At which frequency band I am not able to reach here anything, I will just enhance that frequency band, and I am not going to touch other frequency bands. That is one way of doing it. Okay. So what we are basically doing inside this one, inside the controller, as this is a miniature device, so we need some kind of adaptive mechanism. Okay. Why adaptive mechanism? It should cancel it, and it should cancel it in a dynamic environment. So suppose I am wearing a hearing aid, normal, it is working fine. Now I will put my phone over here. So it will change everything, all the environment. So it should adapt. Okay. Suppose I am sleeping while wearing a hearing aid. With the cushion, again the path is changed. Okay. If females are wearing the hearing aid because of their hair or because of cap, again the path is changed. So we need some kind of adaptive mechanism. So here the neural network came into the picture, or you can say your ML algorithms. So since it is a miniature device, very less power, छोटी वाली बैटरी आती है. Okay, I am not able to run many high computational thing like CNN or anything over there. Okay, so we need only single layer neural network. We'll start with single layer neural network. How we can start from single layer neural network and where we can take it. Okay, so what is a single layer neural network will look like? We'll have some inputs, some weights. Okay, they all add them together. We'll have some activation function, which is usually fixed, and then we'll compute the error and update the weights. This is the basic mechanism of a single layer neural network will look like. Okay, so this is my input. So what we have, input is multiplied by weights, we get the output, which is passed to activation function, and then we have a desired signal. We'll subtract it from the desired signal, and we'll get the error, and we are going to update the weights. Now, in this, we usually use the error function like e square or half of e square. Okay. How we are going to find the weight update rule? How we are going to find the weight update rule? We are going to minimize the cost function. We have to minimize the cost function, है ना? मुझे error minimum करना तो अब क्या करना है? Minimize the cost function. Here we are using cost function as the error square. Error square means basically मैं power error का कम करना चाह रहा हूँ. ठीक है? We differentiate it with respect to weight because this is the only parameter which I can change. I am not able to change the input. I can only change the weights. That is my end. So we are going to differentiate with respect to weights. Okay. Now after differentiating, this is the weight of weight we will get, where eta is nothing but the step size, xn is the input, and en is the error. Okay. This is how a single layer neural network will look like if we make the whole system adaptable in the real world. Okay. This is how an adaptive hearing aid will work. So first we had seen normal analog, then analog programmable with digital control, then digital hearing aid. Inside digital hearing aid, this is adaptive digital hearing aid. Okay, it can adapt with the nature. Okay, now another problem is, are you all aware of ANC headphones, Sony, Bose? कुछ आता है ना market में, and they are saying that active noise cancellation. Okay, so why we need over here? Because in the hearing aid, if you closely watch, there is a gap. If you put the hearing aid, there is a gap, and there is three type of sounds are coming. One is directly coming from the noise source. Okay, another one is और क्या है? और यहाँ पे ट्रैक्ड साउंड भी है जो रिफ्लेक्ट होकर आएगा. ठीक है? And what I want to listen only to the sounds which is picked by the microphone. I am not interested in the sound which is coming from the leakage. That is like an additional sound. Why I don't need that? Because it might be possible this one is a delayed sound, this one will come before. So it is like a reverberation जैसा लगेगा, है ना? कि वही साउंड बार बार आ रहा है, पर कैसा लगेगा? या इको की तरह फील होगा. If it is there is more delay, it will feel like echo. So we need to cancel that one. So for that we can put an ANC over there. How ANC will work? ANC's work is like we'll have a microphone, we'll have a loudspeaker, and let's say this is the primary noise source. And we have a microphone over here also, which will check how much noise is getting cancelled. Now how ANC's work? It will pick the sound, means the characteristics of the sound we want to cancel. The controller will be there, which will generate the anti-noise, and there is a error microphone which will check how much noise is cancelled. So this whole thing is happening in the acoustic domain. Okay. Acoustic waves, how the acoustic waves are propagating, it is nothing but the pressure vibrations. Okay, compression and air pressure. Our ears are basically sensitive to this pressure vibrations. We'll see how our ears work. What is the inside our ear. Okay. So this is one part of work. Then there is something which I had just said that why the headphone is going to amplify sound coming from all the direction. Why not it will amplify sound only from the direction where the user wants, from the 0 degree. Yeah? So for that we can bring a beam forming into the picture. How a beam forming will look, if you see closely, this is a beam forming hearing aid will look like. Okay, what it will do? So beam forming hearing aid. So before making a beam forming hearing aid, we need. I usually use this kind of setup in which the sound is getting played from all the directions. Okay, and I need to tune my hearing aid in such a way that it will pick sound only from the 0 degree, while it will not pick sound from other degree. Okay. So what we have, so let's say this is my dark zone and the other sides are my light zone or unwanted. And we just have this kind of cost function which we are going to minimize. And this is the setup which I had used with the 4 microphone over here. And this is the impulse responses. And this is how the beam forming will look like. So if you closely watch it, you can see that it is not amplifying sound from 30 degree or from 60 degree to 300 degree. It is only amplifying sound from this direction.
सर एक छोटा सा डाउट था कि what if the sound source which is at 0 degree it is at farther distance than the other one, so will the distance will matter
Yeah.
or not?
Now, if it is farther from the other one, it will just make a loop in that direction. Okay.
Sorry, how?
Okay, so it will be like this one. Okay, so if you are saying that if it is more far, whether the loop is getting to cover it or not. This is the question. So the thing is, the gain is not like a 0 or 1 over there. So the beam is not like 0 or 1. It is, the gain is reducing slightly. So if suppose I had made a beam for a 1 meter range, okay, so I had made a beam when I am making a hearing aid, I had designed it for 1 meter range. And suppose in the real world, the person is standing in a distance of 2 meter of range or 3 meter of range. So what will happen? Okay, there are two cases. Either I can have a setting in the microphone in my hearing aid so that I can change the range. That is one way. Or if there is nothing like that, what will happen? It will peak but with a reduced gain. With a slightly reduced gain. So what is this one? This one will showing that how much gain over the frequency band. Over the frequency band I can achieve with respect to other direction. Okay. So how it works? So this is one of the idea by the Siemens in which they are using a gun array microphone. Okay, this is similar to how when we put a specs on the top of our ear, this is how it looks like. Okay, slightly uncomfortable, but this is how it looks like, a gun microphone array, in which they have around 4 to 5 microphones over here. Okay, so what it will do, it will form a beam towards the 0 degree. Okay, how it works? So suppose if we have these 5 chairs and I am speaking from this point, the person sitting on this chair will receive sound earlier than the person sitting next to him, and the person sitting at the end will hear sound after very delay. Let's say after some delay. So what will happen? There is a delay in each person, and we are not able to measure it because the sound is traveling with a speed of 343 meter per second. Okay. So what we can do is like this microphone is receiving sound, this. So everyone is receiving sound at different time instantly. So why not we delay them in an equal amount and then add them together? So उससे क्या होगा? After delaying, they all are aligned. When we adding them together, it will increase the gain. है ना? It will increase the gain. Okay? So either I can use the increased gain directly from here, or I can divide it by the number of microphones. I can use this one directly. What is the benefit of this one? Because the signal of interest is always correlated with each other, but the noise is not correlated with each other. ठीक है? Noise हर point में अलग अलग होगा. So when we average it, it will be divided by m. So noise is reduced, automatically signal is increased. So I can say that my SNR is improved. My signal power is improved, my noise power is reduced. So if you all able to listen, there is a sound is coming from some light. Okay, it's coming. And if I'm going to record it with, let's say, 5 microphones over here. Okay, and I know that whatever I am saying is correlated in all the 5 microphones after some delay, but this is not correlated. Okay, there is a change in pattern over there which is not correlated. So what will happen when we then add them together, divide by m? My overall signal is remain same. The power of this noise could reduce by 1 by m, or if I am using 5 microphones, 1 by 5. So automatically noise power is. So this is the setup which I had used. So there, if I'm not using any directional array, what it can do, whatever microphone is speaking, it will just amplify. So it will amplify all the sound from all the directions. So if you're hearing a normal hearing, it what will do? It will amplify that sound also. Whatever I'm saying in microphone also. If anything, if more machine is running outside, that sound also, it will going to amplify everything. Okay. So we added a new feature where it can amplify only the sound coming from the front, from the 0 degree. This is what we had done. Okay. Now, further, what is the next step where we can take it further? So suppose my ML algorithms, or you can say my deep neural network algorithms or CNN algorithms are able to understand or differentiate between the car noise, alarming sound. Okay. Now, if let's say this person is hearing this and there is a alarming sound from the backside, it might be possible that he is not able to listen that sound. Okay. So we need to design some kind of system, or suppose this person is tuned his gain only to a 0 degree, and there is another person also standing here and he also wants to speak to him. Okay, so why not it will be tuned accordingly, automatically, from which direction the sound is coming, from where, whether there is any kind of alarming sound or not. Okay, or why not we can make it more one level above to suppress a particular sound, to suppress a particular, let's say, car noise, let's say washing machine noise, any home appliances noise. Why not that particular sound is cancelled but everything is remain same? So even if we are sitting in this room and there is some mobbing or some work is going on, we are not able to listen that sound. Why not we can cancel or remove only that particular piece of sound from the sound stream? Okay, so we can bring that by including AI into the picture. So why, however, we can go for a selective noise cancellation. Only in that only a certain type of noise is getting removed. Okay, certain type of noise. It can be fan noise, AC noise. Okay, only a certain type of noise. While the rest of the things will keep into the input or keep there in the input sound stream. Okay. So what are the features we are going to use in that one? This is something which is used by one of the Bose early product, which is not successful because it will take a lot of time to be processed and bring it into the in the real time. Okay, it will take a lot of time. So still everyone is struggling how to bring it in the real time because there is so much processing is on the background. We'll see how it needs so much processing. Okay, so what are the features we are going to use, or what are the features we usually use when we are talking about audio in health applications or audio in AI? Spectrum, spectrogram, spectrum, mel frequency, or gamma. Okay, MFCC or DMFCC. So this is how a normal sound wave or recorded wave will look like. You can record it on your phone. It will look like a one-dimensional series of waves which are increasing and decreasing. Okay, and from these waves we are going to expect feature. So first feature is spectrum. Spectrum is nothing but the Fourier transform of the input. What are the frequencies present? Simple. What are the frequencies present in the signal? This is what we do. So why we are using this feature spectrum? Because as a human being, we are also doing the same thing. How we are going to able to understand the sound. So inside our ear, if you see, we have a lot of hairs, and these hairs are basically vibrating at different frequencies. Okay. So larger the hair, larger the hair, lower the frequency, and shorter the hair, higher the frequency. Okay. So these shorter hairs will vibrate at higher frequency, and this uh, larger hair will vibrate at lower frequencies. This is how we process the sound. Okay, we already doing some kind of Fourier transform inside our ear to understand the sound. Okay, now what will happen if this ear is getting damaged? The person is not able to listen. Then what we can do? We are going for conductive waves. Collateral implant will vibrate the we are directly going to vibrate the bone over here. Okay. So you can you might feel that if you are using a home theater system or in theater, you will feel the vibration of the sounds. Okay. By vibration only you can understand that some music or something is getting played. Okay, so there are two ways. We can send auditory signal to our brain. One is from the ear, another one is from the vibrations also. Okay, so if my ears are damaged, I can go for conductive wave techniques. So why we use spectrum as a feature? Because as a human being, we are also using the spectrum or the Fourier transform. The second trick is the spectrum. Spectrum is coming from the spectrum only. If you just reverse this term, CEPST is just the spectrum is nothing but coming from the spectrum. Okay. Why we use it? It will find the periodicity in the Fourier domain, in the frequency domain. Is that there is any periodicity over there or not? Now, we as a human being, you will also feel that we are more sensitive to the lower frequencies. Okay. If there is a 100 hertz sound and a 500 hertz sound, we can find the difference between them. But if there is a 2000 hertz sound and a 3000 hertz sound, we are not able to find any difference. Okay, it means we are sensitive towards the lower frequency. Okay, an example of that one is our human speech range is from 300 hertz to 3.3 kilohertz. Lower frequency range 300 hertz to 3.3 kilohertz. And by using that frequency range only, we are able to understand whether person A is saying or person B is saying. It means we are more sensitive towards the low frequency. We do also we can hear frequency till 20 kilohertz, but we are more sensitive and more information is present for us only in the low frequency range, or we are more sensitive, or we are providing more or better resolution for that frequency range. Okay, why not bring that thing as a feature, extract as a feature, and teach the machine in the same way how we perceive the sound. Okay. So for that we have something called MFCC. Okay. We have male frequency sextant coefficients for that. What is there in MFCC? It's same as the Fourier transform which we had seen, but with a slight change, because at every instant we have a set of frequency components. So let's say if I am saying A, in that A also I can divide it into 20 milliseconds frame, and in that frames we have some set of different frequencies present. Okay. So why not we use it? So in Fourier transform we get only the frequency information. है ना? We get only the frequency, what are the frequencies are present. But in short-term Fourier transform or MFCC, we can also get what are the frequencies present at different instant of time. So how we are going to do it? We have to divide the whole input frame into small frames. So we use a window technique, and then we find the Fourier transform. Then, as a human being, we provide more resolution to the lower frequency bands. So we have small filters so that it can filter the input into smaller frequency regions for the low frequency. While for the high frequency, what it will do, we can have a larger filter band because we don't need resolution at the high filter band. Okay, and then we just do the DCT because we want the values in the real domain. Okay, and we will take the 13 FCC coefficients. So in the one axis, we'll have the time. In another axis, what we have? We have the 13 MFCC coefficient. So it will look like an image. One axis is time, another axis is coefficient. This will look like an image. And this is the conversion between the mel and hertz. Okay, we just put the F over here, whatever different frequency components, the filter bank we implement by using some mathematical formula. This is the mathematical formula. Now the thing is, they are coming with in mel frequency band, we have a kind of triangular filter bands over there. And the scientists or the researchers have come up with the idea that that is not a correct simulation of the correlate. Why not we come up with more realistic filter bands? Okay, so if you see closely, this is not triangular, this is kind of Gaussian. Okay, this is not decreasing very fast. This is have a kind of a curve structure. Okay, we call it gamma tone frequency band, and this is give a more appropriate simulation of how the our correlate works. Okay, or how our correlate divide the input into different groups. Okay, basically is the reason here. This is a simulation of our air. Okay, at low frequency we'll have more resolution. At high frequency we have chorus resolution. Okay, this is why you can see that the filter bands over here is of wider range at high frequency, while narrower at the lower frequency. Okay, clear? Okay. So once we have the audio feature, okay. So this is what Bose and there are some more companies who are doing it. But the problem is, if you closely watch it, the seconds of data is somewhere 5 seconds, 4 seconds. So for doing that, I need 5 seconds, 4 seconds, or sometimes even 20 seconds in a very noisy zone. Okay, I need to wait for that much time to record the data. Okay, that much time to record the data. So it is kind of slow for real time. And if we are bringing, and if you want to bring it in the real time, we want it to operate in the real time, we need to go for some kind of adjustment which is not the actual result which we want. Okay, that is a problem over there. So this is where everyone is struggling how to bring this 5 second data, why we have to wait for this 5 second data. And then this is going to, once we have the feature, we need a classifier also. And that will again take some time. Okay, this is a bottleneck where everyone is struggling. Okay. First is feature extraction, after that we need a set of CNN. Okay, so there is one way of doing it to make it this our single layer neural network, make it more aggressive. Okay, what we can do is our my single layer neural network have the inputs, weights, and an activation function. Why not we can make this activation function adaptive? Like parallel strategy, why not we can make this activation function adaptive? Why it is to be fixed? So we see that our usual way of finding the weight is error is y of n minus d of n minus y of n, where y of n can be written as phi of s of n. This is some function of s of n. Why not make this function as a object? Okay. So what they come up with an idea that let's initialize as a linear preprocessor into sample of knots, and then we are going to update its knots at every second. Okay, how it looks like? If we are going to update it, it will be something. So here my activation function is what? Linear. Okay. When suddenly my system will become non-linear, my activation function shift. It will make non-linear. So this is another adaptive feature which we had used. Now the second thing is to reduce the complexity so that it can be done in real time. What we have done, if you closely watch it, we have only 4 red dots over there. So only these red dots are updating at every time. Okay. And when the system will become non-linear, it will change its state. So this is the add-on feature which we can bring to make our system more adaptive. But still it is adaptive, it is not bringing that feature thing to cancel that particular sound, okay, or to remove that particular noise from the sound stick. What we need now we need CNN. Okay, there are low complex versions of CNN, where we can reduce the number of parameters by 75% and achieving the same result. Okay. So first for that we need to understand what is CNN. Okay. I think you all are aware of some information what is CNN. Okay. So in CNN we have one कितने layers होते हैं? किस तरह के layers हैं? One is something called convolutional layer, then cooling, convolutional relu, cooling, then pattern, fully connected, and softmax layer. So how many layers we have? We have something called convolutional layer, cooling, convolutional layer, cooling, pattern, fully connected, softmax. Okay. Now the thing is when we are going to write the code, the main problem which we are facing is matrix size is not matching. Okay. What will the size of feature map we have? So we'll see from a simple example that if I have an input which is of size 28 cross 28, cross 1 means this is a black and white image, only one frame is there. If it is color, it will be 28 cross 3. 3 frames from red, blue and green. Okay, this is how 3 frames will look like, red, blue and green. So in old TV, if you remember, in old TV, if you see it from very close, you will see 3 lines, red line, blue line and green line. And from the combination of that, we are getting a different colors. Okay. The same thing is over here. So we'll see how the size we are computing. So this is 28 cross 28, the size of the kernel. Okay, we'll see what is the kernel, how we are expecting the feature is of size 5 cross 5. Okay, and then we'll see the we have total n1 kernels over here, means n1 different kind of feature map we are expecting. So it will take a lot of time. Okay, then what is the size of each feature map? This is something written 24 cross 24. Okay, so how it is coming? 28 minus 5. 28 minus 5 is how much? 23 plus 1. Hello. यानी कल्चरल को बोलेंगे और पैकेज मैं हाँ मैं हर सर ही मेन देख रहे हैं हर सर को भेज दीजिए हाँ एक ही नोटिस को डालेंगे मैं हर सर को भेज दीजिए So what will be the size? 28 cross 28. So 28 minus 5 is 23 plus 1 is 24. Okay. So the actual formula is size of kernel, input size minus size of kernel plus 2p. P is nothing but padding. We'll see what is padding. Padding is just adding a layer of 0 at the outside. Okay. So 2p divided by s. S is the stride. Means the shift over there. We'll see how it is working. Okay, that is the size. So let's say, we'll see an example. Okay, so here I have an image. Okay, in the image you can see that yellow color is keep on shifting. Okay, so this is the size of image 5 cross 5. Okay, the yellow one is of size 3 cross 3. And it is shifting 1 unit at a time. It means stride is 1. And I have not added any layer of 0 on the outside. So P is 0. So 5 minus 3 plus 2P, where P is 0. So 5 minus 3 is how much? 2 divided by S. S is how much? 1. As it is shifting only 1 unit at a time. And plus 1. So how much it is coming? 5 minus 3 plus 1? 3. The size of the feature map is how much? 3 cross 3. Okay? Now, once we have this feature map, the next thing is called max pooling. Okay, so we have different types of poolings: max pooling, mean pooling. Okay, We can go for max cooling, mean cooling. What is the max cooling will do? A max cooling will have a cooling map. Let's say the cooling map is of size 2 cross 2. Okay? And it can cool anything. So what max cooling will do? From this 2 cross 2, it will cool only maximum value. Okay, from this 2 cross 2, it will cool the maximum value, which is 20, 30, 112, 37. And then we can have something called average cooling. What average cooling will do? We'll take the average value. Why we need this one? So suppose the max cooling is performing two functions. One, it is reducing the features. Second, it is making the system more robust. Okay, so suppose I am making a CNN model which can differentiate between which can capture whether there is a mobile or a remote. Okay, so if I'm giving this as an input, it will find all the features. And the next time when I'm giving this image exactly in the same way, then only it is going to recognize. And if I slightly tilt it, it is not able to recognize. Okay. What max cooling will do? It will only find the maximum value. So even if I slightly tilt it, my maximum value is remain same. It is not going to be different. Okay. It is giving me some kind of robustness over there. So what will happen if I am going for a max cooling which is of size 2 cross 2? So 24 will be divided by 2. It will become 12 by 12. Clear? How the size is changing? 24 divided by 2, it will become 12 by 12. Okay? So this is how the cooling is work. For RGB image, we will have different kernels for each thing, and then we'll add them together, we'll have the picture. The same way which we are doing for the single grid. Okay, now the padding will be of two types. One is called valid padding. In valid padding, we are not adding any layer of zero at the outside. And the second one is the same padding. In same padding, we added number of zeros. So in this, always the size will either increase or decrease. Okay. Cooling, we had seen it. Now the question arises, when we are going to design our own CNN network, what type of cooling we are going to use? Whether it will be max cooling or mean cooling. So suppose the dominant color over here is white. Okay, and if I'm going for average cooling, this is how we got. What it will do, it will find the average over here and find the value. Average over here and find the value. If I go for max cooling, what it can do, it will find only the maximum value, which is white. And what I will get? Nothing. So if in this case, if I'm using a max cooling, I will get no output. I can't use it as a feature. So depend on the feature map, I have to choose whether I will go for max cooling or mean cooling. Okay, the same thing over here. If suppose my feature map will look like this one, and I will be going for mean cooling, I will get no output. It is not going to classify anything. So depend on the feature map, I have to select whether I have to go for max cooling or mean cooling. And the question arises that why not we always go for average cooling? It will be giving me something, but we are not. It will be giving us something, but we are not using it with the full power. It is removing some of the features. That is why, by default, if you go for any CNN model, they will say that we are using average cooling. But in ADT, we have to check the feature map and see which one is in dominant. And depend on that, we have to choose either max or mean. Okay. So once we have the cooling, the next thing what we are going to do, we will flatten it. Okay, we can see it through an example over here. So this is my 28 cross 28, 5 cross 5 is the size of the kernel. Okay, what will the size? 28 minus 5, 23 plus 1, 24. Okay, then I am going for an average cooling. The size of the cooling net is 2 cross 2. The output will be 12 cross 12. Again, we are going for a CNN kernel which is of size 5 cross 5. So 12 minus 5 plus 1. This is 8 cross 8. Again, we are going for an average cooling of size 2 cross 2. 8 cross 8 will become 8 divided by 2, 4 by 4. So 4 by 4 is a matrix, which is a, when we are converting a matrix to a one dimensional array, it will become 16 cross 1. 16 cross 1, 16 cross 1, 16 cross 1. So after this, we need a flat. This is a flattened layer, then this is the fully connected. For fully connected, I am going to join all of them together. So how many layers of neurons over there? 1, 2, 3, 4, 5, 6, 7, 12. Each one is of size 16. 16 to 12 is how much? 192. Okay, then what we need? A fully connected layer. And how much the output is going to classify in 10 classes. So always the weight, size of weight vector is output multiplied by input. So 10 cross 192. Okay? Now another thing is in the fully connected layer, as we have 192 into 10 connections. Okay, so there is somewhere in 2000 connections over there. And for each connection, we have to update the weights. Why we are going for that much weight update? Why not we reduce some of the connections? We call it the dropout layer. What dropout will do is, okay, so to reduce the overfitting, we usually use dropout over there. Okay, what the dropout will do? It will remove some of the connections. And because some of the connections are removed, we are not going to use some of the features. Okay? Because we are not using some of the features, it will reduce the overfitting of the model. Okay, that is the idea over. So this is the part which is still people are embedding in their hearing devices, but it is not well completely because this will need a lot of computational power and lot of time to capture the sound. So to overcome this, there is one way. If you already have a kind of lookup table or a filter bank or a data set at some remote location, we'll send the signal, we'll take the weights from there, feed it, and again play it. That is one way. So what we are seeing for hearing aid, we can explore the sparsity, we can explore the active noise control technology. We had already explored this microphone array technique where we can form the beam towards a particular direction. And now the hearing aids is moving towards neural networks or deep neural networks for further enhancing the performance of the hearing aids. Okay. That's if you have any query, you may ask.
Sir, can we use CNN for sensory data, like CSP data?
CSP data for
Actually, we have sensor data, like air pollution data, but we are not able to implement CNN on this.
okay, so the easy way if you want to do is like in GitHub already some single layer CNN are there. Single layer means only conventional layer, one pooling layer, fully connected and softmax. Okay, so you can, what they need is they just need your data in particular format. Means as they are running in a supervised way, so they need your input data and the corresponding label data. Okay, you just give them. Okay, when that code is running in Colab, Google Colab, you just have to give the row address, column address of the CSV data, that this column is the input data and this column is the your output label data. It will train for you something. If you are first in the first hand, if you are going to use it, it will give you some output. Okay. After that, you will start tuning it. It will give you the code that if you want to add more number of layers, you can add. There is just one function: convo 1, convo 2, convo 3, layer 1, layer 2, layer 3. Keep on adding it. Okay. Now, at that time of adding, the only problem which we face is size of the matrix. Okay, that is why I told about the size of the matrix. Okay, that is the only problem you will face, that there is a mismatch error and the code will not run. Okay. So for the default case, they already given one code, but once we are increasing the number of layers, you have to manage the size of the feature map. Otherwise, it will always give some error and your code will not run.
Sir, like I'm not very professional in using CNN,
Mhm.
but whatever the works I have already seen in CNN or in the presentation, one very usual question people ask like, how many CNN layers have you used, or how you decide like
Yeah.
how many CNN layers will
Okay,
be
the thing is, this is basically the empirical way of doing it. Okay. Now, there are two questions arises how we can decide number of CNN layers.
Yes.
And how we can decide the size of the kernel in each CNN layer. Okay. By default, we are using 5 cross 5, 3 cross 3, 7 cross 7, 9 cross 9. Okay. How we are going to do it? So for doing that, there is one paper. What they had done, they come up with the idea why not we make adaptive the size of kernel. So initially they will start with 3 cross 3. If the performance is getting increased by using 5 cross 5, they increase the size from 3 cross 3 to 5 cross 5. Adaptively, how we are changing the size of the shape of the activation function. In the same way, they are changing the shape of the kernel. Okay. Also, we know the kernel weights are getting updated. They are also changing the size of the kernel from 3 cross 3 to 5 cross 5. Okay. And then for some set of data which we usually use, they say that for this data we need this kernel size. Okay. But the another way what people will do, they do empirically. Empirical means if I'm using only one layer, I have so much feature, because we can see that when we are using more number of kernels, my feature sizes keep on getting reduced. Okay, it is from 12 cross 12 to 4 cross 12. And if I'm going to further use it, it will become 1 cross 1 or 2 cross 2. You know, if we have only few features to map the whole image, if let's say we have only one pixel to map the whole image, then it is what? Underdefined system. You know, under model, it is not going to classify. And if I'm going to use only one layer, I have so much features. What it will do? Overfitting. You know, if I'm using only one layer, overfitting. If I'm using, let's say, 10 number of layers, only one, underfitting. That is the problem which we all face when we are going for any model or modeling anything. Either we are going for underfitting or overfitting. So if we are using less number of layers, overfitting, more number of layers, underfitting. So the basic thing what people will do, they keep on increase the number of layers empirically, and they see that whether the performance is increased or not. So what they do is like in any paper, they do an empirical study where they start with a 3 cross 3 kernel size with one layer, then 3 cross 3 kernel size with 2 layers, 3 layers, and they see whether the overall accuracy is remains same or it is decreasing. Once it is decreasing, they are not going to increase it. Okay. Anything? Yeah.
Thank you, sir, for the enlightening session on hearing aids and AI in healthcare. Now, I would request Dr. Kamle Kumar to come and felicitate the speaker with a memento. Now you can break for lunch for high tea at 11:30, and we'll rejoin after 20 minutes.